Good morning, everyone. My name is Bhanu. At Broad, essentially, I help with any GATK-related questions. On the forum, so we have a GATK forum. So any questions that you may have, ask us now while we're presenting, ask us during the coffee break or after the day ends, or after the workshop, if you have any questions, feel free to post questions on the GATK forum, and I'll help you out with them. All right. While I'm explaining data preprocessing, please feel free to stop me and ask me any questions that you may have. All right, so this morning, I'm going to walk you through our best practices for data preprocessing. Andre explained how so many things can go wrong with your sequencing data. So now we're going to talk about how do you correct all of those. So there are three main steps to data preprocessing. First, you want to map your data to a reference genome. You want to remove duplicates that Andre spoke about, and then recalibrate the base quality scores. We'll go into details about each of these steps. So what is data preprocessing? Even before that, why do we preprocess our data? Essentially, the rule is garbage in, garbage out. So you give your variant callers unverified reads, your calls, your variant call, the confidence that you have on your variant calls will be that much lesser. So you want to provide your variant calls with as good reads as possible. And so from the sequencer, you essentially just get a huge pile of paired end reads. And these reads are affected with technical biases and artifacts and duplicates. So you essentially want to clean up your reads before you do variant calling. And so on the slide, you can see here, this is the workflow diagram for our best practices for data preprocessing. So essentially, first you map your reads, mark duplicates, and then recalibrate the quality scores. So the first step is to map the reads to a reference genome. What you're looking at here are essentially reads color-coded by which region in the genome they come from. So once you put it through an aligner, it fits each of these reads against the region in the genome that it comes from. For DNA sequencing data, we recommend and use BWA tool. For RNAseq, we recommend star aligner tool. So when you're mapping your reads to a reference, sometimes it's as simple as you can tell which region it's coming from. For example, in region 1 and region 2. There might be some local variants, but it still the aligner knows which region it's coming from. In some cases, in your samples, you have these duplicated regions, and that's when it gets complicated. And so yeah, this is, in simple cases, it just directly maps these and gives it a high mapping quality. In cases where it's a little confusing about which reads come from a particular region, that's when the mapping quality drops. So an easy case would be essentially you have these pile of reads and you know which regions they come from. And in most cases, your genome is pretty different from the rest of it. So in most cases, it's easy to find these reads and map it to specific regions. But sometimes it gets complicated. For example, if your reference itself has duplicated regions. And so then your aligner is confused. Where do these reads fit? Should it go to 2A or 2B? And so to get around this, we have paired end sequencing. So when you have paired end sequencing and there are duplicated regions in your reference, then using the read 1 and read 2 pair, you can fit it on the reference more easily. And so the output of your sequencing is a SAM file, and the binary version of a SAM file is a BAM file. And essentially, this file format has two sections. There's the header, which is common to all the reads in that sample. And then there are records, which are unique to each read. So in the header, you have information such as the version, the sorting order of the reads. In this case, it's coordinate sorted. You have reference sequence dictionary entries to say which of those reference sequence dictionary was used in the sample, and also read group information. And then in your records that are unique to each read, you have the read name, which gives you like essentially the sample name, the flow cell information, the lane information. Then you have flags. This is essentially binary information about the orientation of your read, orientation of the read and its pair, whether it's aligned to the forward or the reverse strand. All that information is given in the flag. And then you have the read position information, you have the mapping quality, you have the CIGAR string. I'll go into more details about that in a second. You have mate information, which is essentially telling you at what position was the mate of that read mapped, and also the insert size. And then you have this read sequence and quality score that come from the sequencer. And you have some metadata, for example, read group information and some other tags. This link is hidden here, but we have a link to the SAM format to get more details of specific tags and other information about this format. So yeah, let's talk more about, any questions so far? Yes.
So it seems like an alignment algorithm now on more and more categories. So do we still need to do any activity to adapt them, like a short read, very short read, before to align?
Do you want to take that question?
So, oh, right, and this is just for the recording. Yeah. So the in a nutshell, no, you don't need to do any trimming. In our workflow, there's early on in the processing, you can mark the adapters so that they will be ignored in the rest of the processing. And anything, like if traditionally you were doing quality trimming, that's not necessary at all, because the variant callers will take the quality of the bases into account. It's actually used as part of the variant calling model. So it's really not necessary to do any quality trimming. And adapter trimming either. The adapters will be marked and recognized and ignored accordingly.
All right. Now to talk about the CIGAR string. The CIGAR string is essentially summarizing the alignment structure of each read. For example, in this example, the CIGAR string is essentially telling you that the first base was soft clipped. There are 3 matches, 1 deletion, 2 matches, and one insertion and another match. When I say matches, I don't mean exact base match. For example, in this case, here it's saying 2 matches, but the bases don't match. Yes? Sorry, can you say that again? Oh, that's just for the next. So this read has these positions. That's just the next base after the read. Okay, so going back to these 3 matches, like I said, these matches don't mean that it's a base match. It's more about that, that the aligner is saying that these 3 bases match against these 3 positions of the reference. That's it. It's not talking anything about base matching. All right, so usually you have a FASTQ file, you map it to a reference using BWA-MAM, and you get this mapped BAM. The problem with this is, where is my read group information or metadata for my sample? And that's not included in the FASTQ file. So if you want to add read group information to your analysis, you need to do it after this process in a very unnatural way. And so to get around that, at Broad, what we do is use a file format called Unmapped BAM, which essentially keeps your read information and your metadata together in one file. And so what happens is it uses this unmapped BAM file, processes it, and then creates this mapped BAM. And then it combines, so this has all the alignment information, and then it combines this unmapped BAM with mapped BAM to include the metadata information using this tool called merge BAM alignment. Andre spoke about sometimes your reads may have some bacterial contamination. So apart from merging unmapped BAM with mapped BAM, merge BAM alignment also does some cleanup of the reads. All right, so we spoke about how alignment is done for DNA data. For RNA-seq, though, it's a special case, because you have these intronic regions that are spliced from the reads. And so if you map these using DNA alignment tool, you'll have these huge deletions in your reads. And so you use a special kind of alignment tool, and we recommend the star2pass alignment tool. It's not on this slide, but star alignment tool is what we recommend for RNA-seq alignment. All right, so that was step one, alignment. Now let's talk about step two, which is marking any duplicates in your reads. Why do we need to do that? For example, you have this one variant in your data that is basically being amplified by your duplicates. And so variant caller will look at that, and it will take it to mean that there is all this confidence for that, evidence and confidence for that one particular variant. And this is essentially inflated. So you want to remove all of these duplicates for that reason. Also, in case of RNA-seq, duplicates give this artificial sense of increased expression. So again, even for RNA-seq data, you need to remove these duplicates. And so how did these, yes?
Go back to the duplicates.
Yeah.
Do you recommend to remove them as well? You have your sample split between two lines, but based on the same library.
Mm-hmm.
So when you add information, you do this separately to the lines. So you want to remove duplicates separately for each line, or combine them and then remove?
Sorry, I'm not sure about that.
No worries, that's an implementation detail. So what we do is that we do the mark duplicate step across all of the lanes, all of the read groups, because there is there are really two types of duplicates. Some of them are at the library level, and you want to be able to identify those. And so by providing all the data together, we're able to do that kind of cross-library, cross-read group duplicate marking. We do it the same way, regardless, yeah.
So
we are just marking the duplicate at this point, yeah, and then we are keeping them. It's additional data, but that's not useful anymore. What do I ones to process?
So it's true, when we're doing the marking duplicates, we're really just identifying which ones we're considering as duplicates. We don't actually remove them from the file. They stay in the data. It's true that technically you could just remove them completely, and there is actually an option. The tool has an option to remove the tools, to remove the reads from the file. We prefer to keep it just because we really hate throwing away data, and it's a little scary because sometimes we want to reprocess things. You could decide to throw them away, but that does mean that you've lost some information, and you've lost the ability to go back and change your mind on how you're going to do it. But yeah, if you're very concerned about storage, for example, you could throw them out. We don't have slides on UMIs in this workshop. We have some information, some documentation that we could point you to. If you post on the forum, then we can get that to you. And I suggest using the forum, because then there'll be a track tickets, and we'll get back to you with that information. It'll probably be Bhanu who gets back to you, but yeah, that's the easiest way to make sure we get that to you. Yeah, go ahead. Sorry, what's instead of BWA? I'm sorry, I'm not hearing you well. The variation craft toolkit? Oh, graph. Sorry. Yeah, we're not currently using graph-based reference, if that's what you mean, or graph-based alignments. Oh, okay. We're not using that yet. There might be some evaluation going on, but I will say about the choice of aligner. So the choice of mapper or aligner is the single most impactful change that you can make to a pipeline that causes batch effects. And so we're extremely conservative in terms of not changing aligner unless we really have to, unless it really gives us a great advantage. Because anytime you change your aligner, the effects on the results is such that if we were to analyze different data sets aligned differently, we get batch effects. And there was a recent paper, I think, about batch effects in 1,000 genomes that kind of highlights that. We're kind of paranoid about that, partly because we process very large data sets. For example, the Nomad call sets at this point is over 100,000 whole genomes. It costs a ton of money if we have to reprocess all of them. And for a cohort like that, you have to have them all aligned in exactly the same way. So if we change the aligner, we have to reprocess all of the data, and we often reprocess a lot of the other data sets sequenced at the Broads for internal groups as well as some of our customers. And so changing that is a honestly traumatic process for us. So as much as I think it's very exciting that there's some improvements made, like graph-based research for alignments and variant calling, I think it'll probably be a few years before we can consider moving to adopting that in kind of a production setting. Does that answer your question? Yeah. I think there was a question there first.
Oh yeah. So could you tell us a little bit about reduce the BAM format? That's something reduce.
Reduce BAM? Oh, so there was a tool called Reduce Reads a few years ago that we were experimenting with for compressing read data, and we have abandoned that one, and it's bad. Don't use it. And that was like 5 years ago, I think, or more. Definitely not using that anymore. However, for compression purposes, we're very happy with CRAM, and so by default in our production pipeline, we produce CRAM files for storage. So we still often have the data as a BAM file for running the variant calling, etc. But for storage, we store everything as CRAM files, and that has made some pretty important improvements in reducing the file size. It depends. It depends on the settings that you use, because you have several different settings, and there's your basic lossless setting where you're not losing any information, and then there's progressively more lossy options where you can do things like compressing the base quality to having just binned base qualities. The more you compress, the more you can gain, but I hesitate to give you a number because I don't have one off the top of my head, but I can look it up. But you can have some pretty dramatic improvements, yeah, sure. I think you had a question?
It's about this batch effects. We
Mm-hmm.
do know that there are batch effects in the data set. Where can we start adding some kind of covariance in that? Right? What is the treatment for that?
Dealing with batch effects, we reprocess everything. Like if we know that we're going to have batch effects like if we know that there's something in the pipeline that is going to cause batch effects, we change the pipeline so that that doesn't happen, and we will reprocess everything with the same pipeline, because the kinds of batch effects that you can have will lead to things like thinking that there's a variant that's unique to a particular population when it's not, and it's just because of different alignment choices. Like it's often different artifacts or the ability to detect some variants in difficult regions that's so influenced. And so we prefer to have, even if it means that we're going to have an artifact in the data, we prefer to have it everywhere, as opposed to having it only in some subsets. So yeah, we've done some work of, so the Broad collaborated with a few other major sequencing centers in North America to define what we call the functional equivalence specification. And so it's a specification of how you do the alignment and the pre-processing in a way that removes batch effects. And if you have a pipeline that's compliant with that specification, you can be pretty sure that any data sets aligned with those pipelines, compliant pipelines, will be compatible. And there's a paper about it. If you Google functional equivalence pipeline, I think it should come up. And there's also a blog post on the GATK blog about it. We really encourage people to adopt that. And the biggest factor was actually the aligner, but there's a couple of additional things that you can do towards that. Any more questions on that? All right. Sorry.
All right. So where do these duplicates come from? There are library duplicates and optical duplicates. Andre went over those details, so we'll move past this. So now going into how does the mark duplicates tool mark duplicates, essentially. What it does is it looks at the orientation of the read and the unclipped 5' position of the first read. It doesn't do per base matching. It just looks at the unclipped 5' position and the orientation of the read and then decides whether it's a duplicate or not. And for paired end read, it'll do the same thing for both the pairs, orientation and the unclipped 5' position. So here are two IGV screenshots, one without any of the duplicates marked, and then here is how mark duplicate works in essentially marking all of these duplicates, and then you have this option in IGV to show you reads after hiding all the duplicate reads. Just to note, that mark duplicates does not remove any reads. It only marks them as a duplicate. There's a tag that it adds to the alignment to show that it's a duplicate read. Back in the day, we had a tool to do local realignment around complex regions of the genome. For example, repetitive regions, as shown in this example here. It would call all of these variants, but then if you do realignment, it sees that there's actually one insertion here, which then clears out and cleans out all of these reads and removes these extra SNPs that I was originally calling. This is a deprecated tool. We don't do this anymore because our variant callers, haplotype caller and mutex2, that we'll talk in more detail about, does this intrinsically. So this is basically a deprecated tool. And the final step of this process is to fine-tune the base quality scores. Why do we do that? Your variant calling pipeline heavily depends on the quality of the bases called by the sequencer. So any errors that the sequencer might have added to your quality scores, it'll get used by the variant caller irrespective. So you want to clean up those quality scores. And for that, we use this tool called BQSR, which essentially detects the systematic errors created by the sequencer. And these could be due to the physics or the chemistry of the sequencing technique itself, or some manufacturing defaults in the sequencer, which causes these errors across the sample. And so BQSR uses machine learning to create an empirical error model, and then uses that model on all the bases in the sample and fine-tunes the quality score. Some of the covariates that it uses is, say, for example, you have two A's in a row, and any read after these two A's has a 1% increased error rate, then it fine-tunes the quality score to say that any base after the first two A's has a 1% lower base quality. And that's essentially shown in this diagram here. You have the nucleotide context on the x-axis. On the y-axis, you have the accuracy, which is the empirical quality minus the reported quality. So the negative values show that the bases have been overestimated, the quality scores have been overestimated. A positive value shows underestimated quality scores. And in most cases, we've seen that sequencers tend to overestimate quality scores than underestimate. And so when you map these pink dots are before BQSR, and and the purple are after BQSR, and then when you compare the reported versus empirical quality, you see that this neat little line that forms after you apply the base quality recalibration. Something to note here is that BQSR does not change the bases. It does not say that, oh, this particular base was called wrong, I'm going to change it. That's not what it does. All it does is fine-tunes the quality score and the confidence of calling a base.
We have this discussion earlier.
Mm-hmm.
The whole genome sequence has these different coverage in different regions. So has this spread score that we are calibrating now has anything to do with the variation in the coverage? Is there, I mean, do we adjust the coverage?
So this is independent of coverage. I mean, this really affects like individual base calls and what quality we have. Now the link that you can have is that if there are some filters. So GATK does some filtering on the quality of base calls. So if they're below a certain thresholds, some bases will just be ignored. And that goes back to the question about trimming. Do you need to trim for quality? No in part because we take the quality of bases into account. So if you have, and I forget what the exact threshold is, but let's say it's a Q10, below Q10 you just ignore all of them. If you're counting how much coverage you have and you're doing it in a way that is aware of the usable quality, you might end up with less coverage than you originally had if you're looking at usable coverage. Does that answer your question? Okay, great. Yes. Yeah, so Bhanu is going to explain how we mask out real variation, and what I suggest is we go through that explanation, and then after that we can address the question of how that applies to cancer samples. Sound good? Cool.
Hopefully the number of variants due to somatic mutation is not as high as all the sequencing artifacts that kind of gets lost.
But yeah, we'll address that.
All right. So essentially what Geraldine was trying to say was that how this error model is created is that first, all the known variants are masked out. For example, we use dbSNP and see what the known variants are and mask those out, and then create the error model on the rest of the variants, rest of the mismatches. So anything that's not a known variant is assumed to be an error, and then the model is created on top of that. Yeah.
And so where the somatic aspect comes in is that you can imagine that when we're masking out known variation with dbSNP, for example, certainly we can't mask out variants that have not been reported previously. So even in germline samples, my sequence will have some variants that are not known to dbSNP and will therefore not be masked. Now, the nice thing is, because the number of bases is much, much larger than the number of variants where that might be the case, you have billions of bases. There's not many reads that will be affected by having a real variant from my previously undisclosed variants. So that will completely get washed out. The question here is, well, if you have a cancer sample with a much higher amount of mutations, is it possible that that starts introducing some noise? What we've seen, and we work with the cancer genome analysis team on that at the time, is that for the most part, we're still not seeing an effect of having more mutations in the cancer context. There's still way more unaffected bases than you have affected bases by somatic patterns of additional variation. However, some of the analysts in the group we work with sometimes use a database like Cosmic to mask out the most common kind of recurring mutations they see in cancer, because there are some things that do come up kind of in the same places. So it is possible to mask that out. But in general, what we see is that it's not really worth doing. At worst, you get a little bit of extra noise in the model, but you can still detect systematic errors. Because ultimately what we're detecting here is systematic errors, where the machine systematically made errors in the same places. Whereas cancer mutations, for the most part, will show up as random mutations. They're not associated with a particular covariates that's in our model, or not as much. And so that's why it's not a problem. Not as much of a problem. Did that answer your question? Cool.
Great. All right. And so finally, how does this show up? How does this information, new base quality scores, show up in your alignment file? You have these recalibrated base qualities, and you also have, you can have original base qualities. We usually remove these original base qualities because to save space. But yeah, if you wanted it, you could have the original base qualities. And that wraps up this talk. Any questions? We can take them in the coffee break next and talk more about it then. All right. Thank you, everyone.